In this video, we're going to take a look at this HP 4192A low frequency impedance analyzer. I recently purchased it from a seller on eBay. They had claimed that it was fully functional. However, when I went to go make my first measurement, I quickly realized that wasn't the case. So I'll show you what's wrong with it. The first thing, this test fixture that I have installed is a 16047A. I took this off of my 4274A because I know it's good, so we can rule that out right off the bat. So what happens is, the first thing you need to do when making an impedance measurement is perform the open and short calibration. So let's go ahead and we'll perform the open with nothing in the test fixture, and it goes through just fine. And then we install the shorting bar in the test fixture, and we run the short, and it fails with E07 every time. Now the manual explains what E07 means, and it says E07, zero open or zero short operation could not be properly performed. However, nowhere in the entire manual is there any other references to E07 in any of the troubleshooting flows or anything explaining what you need to look at to fix that. So I'm going to show you what steps I took to isolate the issue. At this point, I think I already know what it is, but I've put the machine back to the state it was when I first bought it, so I could show you how I got to the conclusion. And the part that I suspect is being faulty just showed up in the mail, so at the end of the video we'll get that installed and hopefully this thing will be fully functional. Okay, so the next thing I did was read the manual for a while longer until I came across this section here, Analog Section Troubleshooting to Assembly Level. And they just have you go through a bunch of steps to try to narrow down the issue, any issue I suppose, because it doesn't talk about the E07 error. And I spent quite a bit of time going through this. In hindsight, you know, things would have been quicker if I understood them a little bit better. The first test it has you do, almost actually number 2, is check the amplitude at various frequencies. And what was happening is they don't tell you if they want you connected to a scope that's terminated at 50 ohms or if they want you using a 1 megohm scope. So I assume they wanted a 50 ohm load. And what happened is that when I ran these tests with a 50 ohm terminator, they all passed. So I just kept going, right? Now, it turns out they don't want you to test it. They want you to test it at high impedance. They don't want you to test it at 50 ohms. So right now I've got it set, let's see here. So it wants, let's try 99 hertz at 1 volt. We should be seeing 2.8 peak to peak. So frequency 99 hertz, oscillator level 1 volt. And we're seeing 5.8 peak to peak. So that's not right. So that should have been the red flag right there for me at the beginning. It would have saved me a lot of time, but instead I had a 50 ohm terminator on there, and that reads 2.92, so it's a little higher than 2.8, but I thought that was okay, so that was a mistake. So anyways, what it tells you, and it leads me right to the problem that I didn't find till much later. It says, if the test signal level is incorrect in either impedance or amplitude phase measurement, check A1K1 and its peripheral circuits. So A1K1, what that does, that's a relay that switches the instrument between phase amplitude mode and impedance measurement mode. So basically this thing is stuck in phase amplitude mode right now, which is when you use those two inputs over here. And what happened is relay K1 is stuck always on. So this section of the manual that talks about the A1 board makes reference to relay K1. It says, as the amplitude phase measurements require a constant signal source impedance of 50 ohms, the K1 relay bypasses the selective source resistor circuit used in impedance measurements. Like I mentioned earlier, I initially had thought the results I was getting were good due to my confusion with the 50 ohm terminator. So at that point I had continued to perform additional tests, and I found this section here, isolation of the range control circuit, and it talks about a failure in the source resistor circuit, and I performed those tests to check the source resistors, short circuit the unknown terminals, and compare the test current levels that it would display on the screen to this table, and they were much higher. So that indicated that there was a problem with the source resistor circuit. Now, if you look at the schematic, it'll kind of make sense. So, let's see if I can get this in focus here. So this is K1. This is the relay that's stuck on right now. It's stuck in the upper position, which keeps the impedance of the machine at 50 ohms according to the manual for amplitude phase measurement. So since it's stuck in that mode, these source resistors, K6 and K7 I think they are, I'm having trouble reading, or no, it's K2 and K3, they're not able to do anything. So we need to fix that relay. Alright, so then I found this flow diagram C in the back of the manual. It wants us to set the function to impedance mode, the frequency to 1 kilohertz, and the oscillator level to 1 volt. And then it wants to know, is the test signal at the unknown H-curve terminal 2.8 volt peak-to-peak sine wave? And the answer is no, it's 5.6. So we go down. Is the amplitude of the signal 5.6? Yes. Check A1, Q8, K1, and U2. So that's the driver transistor, the relay, and the optoisolator for that relay driver. So ultimately, this other step here is where I realized I had made the mistake with the terminator, since it specifically tells you to put a terminator on the connection. Had I followed this exactly how they had it without the terminator, things would have been a whole lot faster. So I'm going to flip this thing over now and show you what I think's going on. Alright, so for this portion of the video, I'm trying something new. I've got a Vuzix M400 smart glasses headset I'm wearing, and I'm recording the video with that. I thought that would make it easier to navigate this work that I'm doing here. So the area that we're looking at is this section under A1-3 cover on H-curve amp. You can see I've already been in there. I've taken the relay out in question, this relay K1, and I've already tested it. It's fine. So over here we have, I believe it's let's see here, U2. So that's the relay that drives the transistor Q8, which drives, or sorry, it's the optoisolator that drives Q8, which is this relay on and off. And I've replaced the relay with an LED on the power section of it. And I also added a jumper here so that I can manually switch between the two modes, the amplitude phase mode and the impedance measurement mode. I did that just to kind of prove that the solution works. Now what you'll notice is this LED is on, right? But the instrument is currently in impedance mode. Now if you watch as I switch the instrument into amplitude phase mode, see the LED got brighter? So I'll get the meter out here and I'll show you what's going on. Okay, so the negative pin of the relay always has minus 15 volts. And the positive pin is what's switched by the emitter of Q8. And if we look at the emitter of Q8 right now, it's showing minus 5 volts. So that LED is getting about 10 volts right now, even though it's in the off state. And now if I go down here and I switch this back into amplitude phase mode, and let's see, so it's at 0 volts. So that thing is fully on. So we should be seeing minus 15 on the positive side of the relay when it's supposed to be off. So here we are, we're back to minus 5. So this relay's still got about 9 volts when it's off. And if you go over to pin 7 on U2, you can see that we're at minus 4.7. That should be minus 15 right now. I'm going to hold that lead there while I switch it back into amplitude phase mode, and you can see it go there down to 0, or just the junction there. Okay. So what you can do to prove that out is you can pin or short pins 5 and 6 here, and not the best connection I got. There we go. So it's off, right? Now it's getting minus 15. Pin 5 is the supply. So I think this is bad, and we're going to go ahead and replace that here in a minute. Okay, so the question is, what do we use to replace U2? As you can see in the internal layout in the schematic here, the cathode on the LEDs is on pins 2 and 3. On a lot of modern optoisolators, it's on pins 2 and 4, so they wouldn't work. If you look at the parts list here, A1U2, it's HP part number 1990-0577. That's not for sale anywhere. I did find one at Sphere Research in Canada. They're closing down soon and the shipping made it not worth it, so I really wanted to find a new modern alternative, especially in case one of the other ones goes bad. And the description for that says Optoisolator, LED photodiode transistor, IF equals 50 milliamps max. So after quite a bit of time researching on DigiKey and looking through the available parts, I found this Avago or Broadcom, which is actually Agilent and ultimately HP back in the day. HCPL 2530 and 2531. I made a post on the HP Agilent Keysight Groups.io page, and I want to say thanks to Eve Tardif for doing the math to figure out which of the two I should get, the 2530 or the 2531. This is a really great group if you need any help with HP equipment or want to help other people. And he suggested that I want the one with the higher current transfer ratio, which is the 2531. So that is what we bought, and that's what I've installed here. Okay, I'm back, and I put the new Optoisolator in. I put it in a socket because this PCB seemed a little frail. One of the pads actually lifted a little when I was desoldering the old one. It is a through hole, so you gotta, work the temperature up a bit to get the solder to come through the other side. But I'm happy to report that it works. So that HCPL-2531 seems to be a totally suitable replacement for the original HP part that was in here. Got this section cleaned up and ready to put the cover back on, and you can see here right now the thing's in impedance measurement mode, and you can see on the scope that when I switch it down into amplitude phase mode, the amplitude will jump. So that's good. So if you want to stick around, we'll run through some additional tests to make sure every relay in there is functioning correctly. Another task I performed while I had this apart was I recapped the entire switch mode power supply. I didn't record any of that. It's very easy. It's on the top of the unit. Just heed the warnings and make sure that the capacitors are drained and all that before you touch anything. I replaced all of the electrolytic caps on it. If you have this apart, you should at least replace, there's 3 REFA caps. They're 0.015 microfarad. The yellow REFA paper caps that are known to explode, especially if you live in a 240 volt country. I use these. You can see the part number there. These are polypropylene. They're Y2 rated, so they are totally adequate. They might actually be X2, Y2. Okay, they're Y2, X1. Not sure if you can read that there. The originals were just Y2, so that's a good thing to perform. Alright, and I also fixed up the test fixture. It is a 16047C. It was missing one of the BNC levers. I want to say thanks to DefPalm for putting the 3D model online. That was a lot of fun to get apart. I'll put a link or a picture up on the screen to show you how I got the plates out there. And I also 3D printed some knobs. I just used a knob generator. These had the brass part on them. It was just missing the plastic, so that'll work for now. So remembering back to the manual, there was the test here with the current when selecting the range manually. So what that'll do is that'll validate those other couple of relays in the source resistor selection circuit. So the first thing I'm going to do is I'm going to perform the 0 open and 0 short. So here's open. Okay, and put the shorting bar in here. And this is the type of test fixture you have to tighten down, which is nice. And short. And we can see that is now happy. So to perform this test, it wants us to set the spot frequency to 1 kilohertz. And now since I just turned this on, it defaults to 100 kilohertz. So we'll hit spot 1 kilohertz. Oscillator level 1 volt, which is on by default. And it wants us to set the ZY range to manual. And what we're looking for is in the 1K range, we're looking for 10 milliamps. So to set that to manual, we'll hit one of these here. So we want the 1K range, which would be, I believe it is this one. And we'll turn on the test level monitor in milliamps. And we are at 9.7, close enough to 10. Okay, and then let's go to the 10K range, which is looking for 1 milliamp. Okay, 1.16, and the 100K, and that's looking for 0.1. We're at 0.119. I'm happy with that. This thing might need a calibration, but that's much better. Close enough for now. Okay, and then let's throw a couple parts in there and see how they measure. And I'll actually put the 4274 in the frame too, and we can, test the same frequencies for a few of these parts. Alright, we're going to test out capacitance mode. I've got a few capacitors here. They're silver micas, 10 picofarads, 100 picofarads, and 1000 picofarads. So we'll start with the 10. They're both set to 1 kilohertz and 1 volt. So that's reading 10.1 in the 4274. And let's switch this into capacitance mode. This one I've got to screw down. Alright, it's reading 10.3, 10.2. Okay, let's try the 100. 101.1. 101.2. 4274 is nice. It definitely gives you a bit more resolution, but that's not the reason I bought the 4192A. And 1000 picofarads. 1003.6. And 1003.7. So they are pretty close, and I am happy with that for my needs. So with the 4274A, you get to choose from a bunch of frequencies that are predetermined: 100 Hertz, 120 Hertz, 200, 400, 1 kilohertz, 2 kilohertz, 4 kilohertz, 10 kilohertz, 20, 40, and 100 kilohertz. I have a 2200 UF microfarad 63 volt capacitor in there right now, so I'm curious to see 120 hertz. One thing you'll notice with the 4274A, it has a high resolution mode, and it's showing 1.9526 millifarads and 71.79 milliohms of ESR. The 4192A doesn't have the ability to go into a high resolution mode. Let's put this down here. It does have an average mode that seems to give you a little bit more resolution. So I've got this in here, and you can see there's not as much resolution, especially on the ESR. That's okay though. The reason I got this is because you can key in any frequency from 5 hertz to 13 megahertz, and you can do sweeps of it on the computer with some software that somebody wrote a few years back. So it's pretty cool. You can also bias the capacitor with an internal bias source. On the 4274A, you can bias it with an external power supply by selecting some switches on the back. There's an option for an internal bias source, which mine doesn't have, but it still requires an external controller, whereas this is all right on the keypad. So I can see, let's see this capacitor, let's see what it shows at 60 hertz. 1.965 millifarads. I'll go down to 5 hertz even. It's going to take a minute to refresh. .9987. So I'll show you the sweep software on the computer here. Okay, I have a 4.7 microfarad 100 volt Nichicon UVZ capacitor in the test fixture. Here's the part number. And we're going to perform a sweep from 10 hertz to 100 kilohertz. The name of this software is 4192A Sweep Utility, and you can download it online for free. I'm using a National Instruments GPIB USB adapter. He has an all-in-one installer that installs all the drivers and packages to make it a lot easier, since it needs some runtimes from like 2013. So with this tool, you can control the whole front panel of the instrument. You can do spot readings with this section on the left here and just read them out down here, or you can perform a sweep. And I'm going to perform a sweep from 10 hertz to 100 kilohertz. So we'll go ahead and hit the sweep button, and we'll see that data start to populate. The red line is the capacitance and the green line is the ESR. And you can see as the frequency increases, the capacitance decreases, and the ESR also goes down. I've got averaging turned off, so this should go pretty quick. This is much nicer than having to spot check at a couple different frequencies on the 41 or 4274A. It's also nice that it goes beyond 100 kilohertz, so I don't have to buy a 4275A. Not that I need that for the majority of the work that I do. And there it is. There's our plot. So you can do what you want with this data. There's different ways to interact with it in this tool, or you can export it, which I haven't tried yet. There's also this data fit section of the utility, and I don't know how to use that yet, but hopefully I'll grow into it. Alright, that's it for this video. As I learn more about this tool, I'll maybe share another one in the future. If you have any questions or suggestions, let me know in the comments. Thanks.